Welcome to my channel. In this video, I'm gonna go over acid base chemistry of amino acid. Alright, before going into acid-base chemistry of amino acid, there are a few things that you have to remember. Things to remember. Number one, if pH of the solution is less than pK, then the carboxyl and amino group, both they are in protonated form. And second, if pH is greater than pK, then they are in deprotonated form. Number three, third thing that you have to remember is the protonated form of carboxyl group has no charge, but the protonated form of amino group has +1 charge. Fourth thing that you have to remember is, so these are protonated form. The deprotonated form of the carboxyl group has -1 charge, whereas the deprotonated form of amino group has no charge. So these are deprotonated form. Alright. So I want to go over pK. What does pK means? pK simply means the pH at which there is equal number of protonated form of any species. Equal number of protonated form of that species to deprotonated form. For example, this example of carboxyl group, the pK of carboxyl group means the pH at which there is same number of COO minus versus COOH. So that's pK for carboxyl group. Alright, now we're gonna go over acid-base chemistry of uncharged amino acid. Uncharged amino acid. So remember, this is the general structure of amino acid. So uncharged means this R group has no charge. So it is not involved in acid-base chemistry here. So let's say this amino acid, this uncharged amino acid is in a beaker here. It's uncharged amino acid. So let's say the pKa right now here is very low. It is so low. It is so low that it is lower than pKa of carboxyl group and amino group. So let's say lowest pH. So what happens? If there is lowest pH, then this carboxyl group is protonated. R group is not involved here. And amino group is also protonated. That means this has charge. So the overall charge of this amino acid is +1. So now as we increase the pH of this solution here, so that the pH is in between the pKa of carboxyl group and amino group. So it's higher, the pH is higher than the pKa of carboxyl group, but lower than the amino group. So then what happens? Let's say that pH has a moderate pH. What happens? As we increase the pH above the pKa of carboxyl group, this becomes deprotonated. But the amino group still is protonated as the pH is lower than the pKa of amino group. So the overall charge of this amino acid is 0. Now this form of amino acid is called deuterium form. By definition, deuterium form means the amino acid has both positive and negative charge, but the overall charge of the amino acid is 0. So this is a deuterium form of this amino acid. As we increase the pH of the solution above the pKa of this amine group, what happens is, so highest pH. So this carboxyl group is already deprotonated. Now this amine group is also deprotonated. So the overall charge of these amino acids become -1. So now this amino acid went from +1 to 0 to -1. When it went from +1 to 0, it crosses pKa of carboxyl group. And when it went from 0 to -1, it crosses the pKa of pKa of amine group. So now what is the isoelectric point of this amino acid? Now the isoelectric point by definition is the pH or pK at which the overall charge of the amino acid is 0. So if we divide the pK value nearest to 0, if we find the average pK value, that gives the pi of this amino acid. So that is pK of COOH plus pKa of NH2 divided by 2. Alright, this is the formula to calculate the pi isoelectric point. So this is called isoelectric point. So that's the formula to calculate isoelectric point of uncharged amino acid. So next we're gonna go over acid-base chemistry of charged amino acid. Acid-base chemistry of, let's go over positively charged amino acid first. positively charged amino acid. Alright, so this is the general formula again of amino acid. So let's say this positively charged amino acid is in beaker. Positively charged amino acid is in beaker here. And since this is positively charged, I'm gonna write Rp here for positively charged. So let's say the pH of the solution in this beaker right now is lower than the pKa value of carboxyl group, amino group, and this positive side chain. So then what is the structure of this amino acid looks like? It's at lowest pH. This carboxyl group is protonated and this amino group is protonated and it has positive charge. Now this side chain is also protonated, and since the side chain is also amino group, remember amino group in protonated form has positive 1 charge. So the overall charge of this amino acid is +2. So as we increase the pH of this solution so that it crosses the pKa of, it is above the pKa of this carboxyl group. So then what happens? pH above pKa of carboxyl group. What happens? This carboxyl group gonna lose its proton and the charge becomes -1 here. But still this side chain has its proton and so is this amino group. But the overall charge now becomes +1 because this group loses its proton. Now we again increase this pH of the solution in this beaker. So now the pH is above the pKa of this amino group, right? Amino group here. So what happens? Now pH is above pKa of amino group. This is already deprotonated. Now this amino group is also deprotonated. Remember, in deprotonated form, amino group has no charge. But still, the side chain is in protonated form. Now, the overall charge of amino acid becomes 0. Now, this is the deuterium form. This is the deuterium form of the amino acid. Now, finally, we increase the pH of this solution so that it is above the pH of the above the pKa value of this side chain. So then what happens here? This group already has lost its proton, so is the amino group. Now, yeah, you guessed it right. Side chain also loses its proton. Since the side chain of the positively charged amino acid is amino group, so the amino group in deprotonated form has no charge. So the overall charge of this amino acid in this pH becomes -1. So now what you can write is this amino acid went from +2 to +1 to 0 to -1. So when it went from +2 to +1, it crossed the pKa of COOH group. When it went from positive 1 to 0, it crossed the pKa of NH3 group. When it went from 0 to negative 1, it crossed the pKa of side chain or pre group, R group. So now what is the isoelectric point? Remember, isoelectric point is the average pKa of the average pKa of two nearest pKa of 0. So the overall charge of the amino acid is 0 here, and then two nearest pKa are pKa of NH3 and pKa of side chain. So if we find the average of these two, NH2, average pKa of this two group, this gives the Pi of positively charged amino acid, and this is a general formula to calculate isoelectric point of positively charged amino acid. Okay, next we're gonna go over acid-base chemistry of negatively charged amino acid. Negatively charged amino acid. Okay. Again, this is the general formula, general structure of the amino acid. So since we are dealing with negatively charged amino acid, I'm gonna write Rn here. So now let's say this amino acid is in this beaker, negatively charged amino acid. So now let's say the pH of this solution in this beaker is lower than the pKa of every group in here. So at lowest pH, what happens? So at lowest pH, so if pH is lower than the pKa of this group is protonated, and this group is also protonated, and side chain is also protonated. So the protonated form of amino group is positive 1. Remember, negatively charged amino acid, the side chain is carboxyl group. So the protonated form of carboxyl group is uncharged. So these two are uncharged. So now the overall charge of the amino acid is positive 1. As we increase the pH of the solution above the pKa of carboxyl group, this carboxyl group, what happens is that carboxyl group gonna loses its proton. So deprotonated form of carboxyl group has negative 1 charge, but the side chain still has its proton because the pH is lower than the pKa of side chain, still in this case, and the amino group still has its charge. So the overall charge of the amino acid becomes 0. Now this is the deuterium form. This is the deuterium form of the amino acid because the overall charge is 0 and the amino acid has both positive and negative charge in it. So now next we're gonna increase the pH such that it is above the pK of this side chain. So now what happens is this already lost its proton. Now this side chain gonna lose its proton. Remember, the side chain is carboxyl group here, and in deprotonated form this has negative 1 charge. but the amino group still has its proton, so it retains its positive one charge here. So the overall charge becomes -1. So now as we increase the pH of the solution, now pH is above the pKa of this amine group here. Now in this case, amine group also gonna loses its proton. So when it loses its proton, remember amine group in deprotonated form is uncharged. So now the overall charge of this amino acid become -1. So this amino acid went from +1 to 0 to -1 to -2. So as it went from +1 to 0, it crossed the pKa value of carboxyl group. As it went from 0 to -1, it crossed the pKa of the side chain. As it went from -1 to -2, it crossed the pKa value of amine group. So now what is the isoelectric point? Now remember, isoelectric point is the average of the pKa nearest the 0 value. So that means pKa of carboxyl group plus pKa of side chain divided by 2. So this is the general formula to calculate PI, isoelectric point of negatively charged amino acid. Okay, so now I'm gonna summary here what we went through just now. So the PI of uncharged amino acid. PI of uncharged amino acid. What is the formula? pKa of COOH plus pKa of NH2 divided by 2. And this is always approximately equal to 6. Now isoelectric point of positively charged amino acid. So this is pKa of amine group plus pKa of positively charged group side chain divided by 2. Now this is approximately always greater than 6. Now PI of negatively charged amino acid. This is pKa of carboxyl group plus pKa of negatively charged side chain divided by 2. Now this is always approximately less than 6. Alright, now I'm gonna go over some example problem here. Okay, this problem we are given extra glycine here. Remember, glycine is H here. So we are given pKa of this amino group, which is 9.60. pKa of this carboxyl group is given, which is 2.34. Okay, what is find the PI of glycine. Remember, glycine is an uncharged amino acid. So we know PI to calculate, the formula to calculate PI of uncharged amino acid is pKa of COOH group plus pK of amine group divided by 2, which is 2.34 plus 9.60 divided by 2, which comes out to be 2.34 plus 9.60 divided by 2, which is 5.97. So that's the answer for the first part here. Now the second part is asking structure of glycine at physiological pH. Remember, physiological pH is 7.4. So we are given pH is 7.4. Now this pH is above the pK of this carboxyl group. That means this carboxyl group is in deprotonated form. Now we don't worry about the side chain because this is uncharged. Now 7.4 is lower than 9.6, which is the pK of this amine group here. That means this amine group is in protonated form. So this is the form of amino acid, structure of glycine at 7.4, and this is Zwitterian form too. Zwitterian form. All right, next we're gonna go over next question. All right, okay, this is asking about lysine. Let's try structure of lysine here. NH2, 1, 2, 3, 1, 1, 2, 3, 4, and then fifth one is amine group. Okay, this is lysine. What is given? So this is given, which is 2.18. The pK of this group is given, which is 8.95, and the pK of side chain is given, which is 10.53. All right, so we know pi of uncharged, pi of positively charged, because lysine is positively charged amino acid. Pi of positively charged amino acid is pKa of amine group plus pKa of side chain positively charged divided by 2, which is 8.95 plus 10.53 divided by 2. This equals 8.95 plus 10.53 divided by 2 is 9.74. 9.74. Okay, so the next part of question is asking draw a structure of lysine at pH of 12. So pH is 12. So 12 is above 2.18. That means this group is in deprotonated form. And remember, carboxyl group in deprotonated form has negative 1 charged. And 12 is also above the pK of amine group. That means this is also deprotonated form. The deprotonated form of amine group has is neutral charge. 1, 2, 3, 4. And 12 is also above the pK of the side chain. So the side chain is also in deprotonated form. That means no charge, it is uncharged. So the overall charge of this amino acid at pH of 12 is -1. And this is the structure of amino acid lysine at pH 12. Alright, next we're gonna go over another question. Okay, aspartic acid. Okay, I'm gonna draw a structure of aspartic acid here. Okay, what is given? pK of this is given 1.88. This is given 9.60. And this is given 3.65. Okay, aspartic acid is negatively charged. So pi of negatively charged amino acid is pK of carboxyl group plus pK of negatively charged side chain divided by 2, which is 1.88 plus 3.65 divided by 2, which is 1.88 plus 3.65 divided by 2, which is 2.765, 2.76, or we can round up to 2.77. Alright, the next part of the question is asking what is the draw structure of aspartic acid in deuterium form. Okay, in deuterium form, the overall charge of the amino acid has to be 0. So let's say this is this carboxyl group lost its proton, but this one is still protonated. This one is still protonated, and so is this group. So this is the deuterium form because the overall charge of this amino acid is 0. So this will be at pH above 1.88 but below. So okay, pH is above 1.88 but below 3.65. Alright, that's it for this video. Thank you for watching. If you find any value, please subscribe to my channel and also like this video. Thank you.